Okay, let's start. All right. First things first, quick reminder about your exam that's coming up in a couple of weeks. If you're a distance student, if you haven't arranged a proctor yet, go through the instructions on Canvas, email us, let us know. You have almost less than a week, a few days to make the arrangements and let us know. So get to it quickly. And also, starting next week, we are going to have our speakers. Every Thursday, we're going to have a speaker. They typically start at around 6:30. So if you have to miss my part of the class, that's fine. But try to show up for the second part because you're going to get bonus points for it. So for distance students, that would constitute logging in through Zoom. We're going to get a snapshot and we're going to take care of attendance that way. But that only counts if you are a distance student. If you're a distance student, you want to come to class, you're welcome to, because sometimes you get to interact with the speaker after the class and during the break, and a lot of opportunities may arise from that. So if you want to come to campus, feel free. We would love to have you. What else? Oh, next week though, we start a little bit earlier with our speaker. So 6:15 instead of 6:30. So if you have to miss my part of the class, it's okay. Try to show up in time, 6:30, 6:15, to don't distract the speaker when they start. Okay, any questions about the speaker, about the guest lecture in general? Okay. I'll try to give quizzes from guest lectures, and depending on the topic that they may cover, we may or may not have questions from the lectures they give in the exam. So be careful, go through them definitely after they show up and they present. And I make all of the slides available to you through Canvas, so you're gonna have access to their slides. And obviously you can have access to the videos on YouTube. What else? I think that would very well cover it. And this year I managed to bring back 3 of our speakers from the last 2-3 times that the classware was offered, and they were some of the most stellar speakers that we've had. So hopefully you enjoy the lectures that they give you, and it's very practical. They have a lot of experience. Some of them have been working in a couple of or more of companies around nearby. So that's another opportunity for networking. All right. So let's get to our review. Design life. What is design life? Either the definition, either or the formula. Let's say I tell you that the design life, if you're interested in the design life corresponding to a 90% reliability, how would you calculate that life, that design life? Perfect, exactly. So it will be the time corresponding to that reliability of interest. Perfect. And with that logic, if I want to get the median, how would I change that function on top? Median is half, right? So I would just set it equal to 0.5. So R Tmet equal to 0.5, and this is equal to also F of Tmet, right? Because half of it is unreliable, like 50% unreliable, 50% reliable, right? All right, MTTF. If I have this PDF, how can I get my MTTF? X. DT, perfect. Okay, from minus infinity, because I wrote everything by T, let's write this also as random variable T. Okay, what's the alternative? We gave an alternative formula that comes handy sometimes, right? ET equal to, do you remember that's based on reliability function? Perfect. All right, so it's integral of the, okay, so there's a catch though. Can we always use this one? Not always. What is special about the random variable if I want to use the second equation? Positive, exactly. So starts from 0. So the random variable is positive. So I cannot always use this, but often in our case should be usable because we work with life life data, right? Variance. Variance of x, variance of t is equal to, how would you calculate variance? No one? Let's start small. E of x squared minus e of x squared. Oh, I'm writing with t. Okay. T squared minus e of t squared, or e of t minus mu squared, or integral, right? T minus mu squared ft pt. This part of my board is dead. Okay, try again. ft pt, right? Minus plus. Okay, makes sense? All right. Hazard function. We start talking about hazard function. First off, the values that I get from my hazard function, for instance, is the value 2 an acceptable value? Should the values that I get be between 0 and 1 necessarily? Function. It's not a probability. It's a rate. It's the imminent rate of failure, right? So be careful about that. It's not bounded by 1 like a probability. It's a function, like a PDF, right? How it's a probability density function. It can go above 1, right? As long as the area. So there we have a constraint that the area under the curve needs to be 1, right? Here we don't have any kind of restriction, right? Because it's okay. So we show it with lambda or h. Let's say lambda t. Do you remember the function we came up with? Ft over r of t. Or if I want to purely write it instead of, in terms of r, I can do that too, right? Because I can write ft in terms of r. That would be minus ert dt over rt. Okay. We also, so okay, so here I'm getting from r, I'm getting hazard, right? But we showed last class that we can do it the opposite, right? We can get r from lambda. Do you remember that formula? If I want r from lambda. Mm-hmm. 0 to t, lambda, I guess lambda u du, right? Okay, good. As long as you know where to find it in your notes, again, it's open note, open books. I understand you don't have to memorize things. But as long as you know which formula to use when, you're golden, right? You're good. Okay, so we talked about bathtub curve. Let's draw a bathtub curve. Something like this, right? We defined 3 zones. Let's say the zone 1, 2, and 3. What am I plotting against what? Hazard function. Perfect. So this is hazard versus time. Okay, so can somebody tell me something about, let's start with the easiest. Zone 2. Can you tell me something about zone 2? What do you notice in zone 2? Can you describe? I heard something. It's linear, it's constant, right? Yeah. So I would say it's constant, right? Because it's the same number as is in my figure, right? So if it's constant, like what else can we say about it? It's called, do you remember what this zone is called? Constant failure rate. Okay, so it's constant failure for the most part, right? Because I'm drawing it to be a constant line. And so it's called useful life, right? Things happen during this time at a random rate, right? So that's the useful life. Okay, let's go to zone 3. What do we know about zone 3? What is the hazard? What does the hazard look like there? It's increasing. So increasing failure rate. What that may be happening? Why is it happening? It's close to end of life, right? It's wear out, it's wear and tear that's happening to the product, right? Okay, so let's talk about the first zone. You remember the names for the first zone? First, what does the hazard look like? The hazard function? Decreasing, right? Okay, so we have DFR. What is the zone referred to usually? Burn-in. What else? Infant mortality, right? The same with essentially humans, right? If you are very high risk to something that happened to you because you're very vulnerable, maybe 0 to 2 months or 0 to 2 weeks, like something like that, right? And then you get to your constant life, you don't die unless you get into an accident or like you fall off the like something, right? And then you like end of life, you have wear and tear. Okay. And we showed different techniques, or at least we described different techniques for addressing reliability in each of these zones. In zone 1, we can do burn-in testing, right? Getting rid of the products that are faulty or have low quality. During the constant life, the useful life, or when we have constant failure rate, we may be using derating, right? We may be using like a couple of motors in parallel to make sure that like we have redundancy in the system. During the increasing failure rate, when we have increasing failure behavior, we may be actually doing derating, right? So maybe like your motor can or like your pump can push through like so much water, and then you are using a lesser amount, something like that. All right, conditional reliability. We said if you have a product, instead of being interested in what is the likelihood that it will last up to some point, or the reliability is some amount, you are interested in the conditional reliability, the fact that it has lasted up to some time t, timeline. If it has lasted up to some time t0, what is the likelihood that it will last for another t units of time, right? If I want to show that in terms of notation, how would I show that? Given RT naught. And then, so this is my shorthand for showing that, right? This says that the reliability that it will last, the product will last another t units of time, given that it has already survived up to t naught, so t0. Right? Okay, so, and how do I expand that? R of t plus t0 over R of t0. Right? So burn-in and DFR hazard. So if let's say I have a DFR hazard, right? We looked at an example where we let a component, I don't remember what type of component it was. We calculated the reliability starting from the beginning, right? And we got a time to failure given a design life, right? We got the design life given a certain reliability, right? And then we looked at the conditional reliability, right? And then we realized that the time is going to be longer. And we said that this is because through burn-in, we are getting rid of the unreliable component, or the part of the component, or the part of the time where the component shows a decreasing hazard function or decreasing failure rate, right? So they're using burn-in for a DFR, when you have DFR hazard, helps increase the reliability of the product that gets shipped, for instance, to the customer. And then some of you may have seen in the quiz that it's not necessarily the case if you have increasing failure rates, right? Your reliability, conditional reliability, doesn't necessarily increase if you have if you don't have DFR. So you have to go through the calculations every time, or just look at your hazard function every time to see if it's DFR or IFR before using burn-in. Right? Using burn-in for an IFR is meaningless. Okay. All right. Then we start talking very briefly about life data analysis. We said that we have always a sample in reliability engineering, right? And then from the sample, we want to pass some judgment about a population. So we get the data, we collect the data about the sample, we try to fit, at least in this class, we try to fit a parametric distribution to it. We estimate the parameter, and then we go back and try to make some judgment about the mean time to failure, variance, some different metrics about the entire population. And through that, we start talking a little bit about different types of data. We have censored data or we have complete data. It's perfect if we always have complete data, but that's not necessarily true. In the field, we may face some kind of like censored data. We talked about singly censored versus multiply censored, right? Field data versus testing. And also we talked about right censored, left censored, or interval censored, right? If we don't have full information, we just know that our component has failed before some time or after some time. We said that that's censored data. So I just wanted you to hear those kind of terminology, and in case you may need it later. Okay. And finally, we introduced the 4 distributions that we're going to cover. So hopefully we're going to go through all of them today, because I'm banking on the fact that you're familiar with normal and exponential. I'm going to explain everything again, but it's going to be relatively quick compared to Weibull and log normal. And we also talked about the parameters of these parametric distribution. We said that in live data analysis, we have 3 main types of parameters, right? Do you remember what the types were? We had 3 types. No? Location, scale, and shape. What does the location parameter do? It shifts the distribution, okay? What about scale? What does scale parameter do? It changes the spread. Exactly. If you have a larger shape parameter, scale parameter, then your distribution is more spread out. And finally, something that's not location or scale is shape distribution. It changes the shape of the distribution generally. Okay. All right. So we're going to go through the lifetime distributions, which are capturing continuous random variables, right? They're talking about life. But we're going to have a couple of digressions because I want to remind you of a couple of discrete random variables, which are going to come handy throughout the class. So the first one would be binomial distribution. I'm sure you're all familiar with it, but let's just very quickly go through it and describe it. So we have a capacitor that remains functional after a month with probability 0.716. Then we are interested in the likelihood that 7 out of such capacitors, out of 10 such capacitors are functional within a month if we are running a test, right? Let's think about it. We have capacitor, let's say 1, 2, 3, let's say 7, 8, 9, 10. Let's say these are my capacities, right? What is the probability that one of them remains functional? I call it success. Non-functional, I call it failure. Success is 0.716. Failure is 1 minus 0.7. Okay, if I want, let's say these 7. Let's say this is success, success, all the way to 7, and these are failures. If I want to observe something like that, what would be the likelihood of that? The first 7 are successful, right? Success, quote unquote, functional here in this case, and the last 3 are not. So it will be the first one survives, and the second one survives, and the third one survives. I'm using and, right? Up to the 7th one survives, and the 8th one fails, and to the 9th one fails, and the 10th one fails, right? I'm using and. Are these capacitors independent? Agreed? No? Yes? Does the fact that one fails impacts the other one failing or surviving? No, right? So they're independent. So I'm ANDing, right, a bunch of independent events. What does that mean? I can multiply them, the probabilities, right? So the fact that if I want to see something like this, I will see the probability of that will be this to the 7, 1 minus 0.716 to the 10 minus 7, or 3. Right, so far so good? Okay, now let's see. This setup, the first 7 succeeding and the last 3 not succeeding, was one of the possibilities of distributing 7 checks over 10 empty spaces, right? So in how many ways can I pick 7 spots out of 10? 10 choose 7. Make sense? So this will be the ultimate probability. Hopefully this sounds familiar to all of you. Okay, so let's formalize that. Here we have a binomial experiment that meets 4 criteria. We have a predetermined number of trials, n trials. The trials are identical, and they lead to outcome. Oh, I skipped. The trials are independent. The trials lead to failure or success with a fixed probability. If we have a setup like that, we say we have a binomial experiment. And then random variable x will give us the number of successes among the n trials. Okay, so I have 2 parameters, n and p, and I show my distribution with lowercase b. So b, x, and p will be n choose x, p to the x, 1 minus p to the n minus x. Right? This is binomial distribution, where my x, what is the range of x? 0 to 0 to? What's the maximum number of trials? Or like, what's the exact number of trials? N. Or 10, yeah, n. Okay. And otherwise it's 0. All right. So we show it with these 2 pieces of notation if I want to do a shorthand. And then anybody remembers E of x and variance of x? Yes. NP, NP 1 minus p. Looks familiar, right? Okay. All right. So let's go to our first distribution, exponential. So f of x is equal to lambda. Lambda is a minus lambda x, where x is greater than or equal to 0. For x less than 0, it's simply 0. And we show it with x tilde exponential lambda, right? We have how many parameters for exponential? 1, right? Just lambda. All right. Here are the mean, variance, and standard deviation. Right? Mean is 1 over lambda, which is exactly the same as standard deviation, 1 over lambda. All right. So when 1 over lambda increases, what happens to sigma? Question. Sure. Mm-hmm. Question. No. This is just a constant. Thanks for bringing it up. This is just a constant. I could write m times e to the minus mx. Right. This is just a constant. Good point. It's not a hazard function. All right. Good. Okay. Go back to my question. When 1 over lambda increases, what happens to sigma? No, 1 over lambda. If 1 over lambda increases, sigma increases. Like super simple, right? But what does that say about 1 over lambda? If I think of it as a parameter, what kind of parameter is this? This is a scale, right? So 1 over lambda is a scale parameter, right? So if I were to write, instead of writing lambda e to the minus lambda x, if I was writing it as like 1 over mu e to the minus 1 over mu x, right? Or maybe I should. Let's not confuse. So 1 over lambda is a scale parameter. Okay. So let's think about it because okay. So let's think about it some other way too. So now let's look at mu. Mu is equal to 1 over lambda, right? What does that mean in terms of lambda? So, okay, let's say the mean time, mu is the mean time to events, right? The mean time to failure or anything. Let's say the mean time to failure is 2 minutes, right? How many of these events do you expect to see in an hour? 30, right? So what is the rate of failure in an hour? 30 per hour, right? So 1 over lambda is the scale, which means that lambda is the rate. But it's not one of the 3 fundamental ways we we name our parameters. But so you can think of 1 over lambda being a scale, or you can think of lambda being a rate of this parameter or of this distribution. So we refer to so if I tell you I have an exponential distribution with rate 5, you know what I'm talking about, lambda. Right? So that's the bottom line. I wanted to tell you the relationship between the mean and rate. All right. So now let's look at the reliability function. So if I have f of x, let's first write f of x. F of x, the CDF, is 1 minus e to the minus lambda x for x greater than or equal to 0 and is 0 otherwise, which means r of x is equal to e to the minus lambda x. Right? Super simple. All right. So let's look at a few plots. Okay, here I have plotted 4 exponential distributions, right? I'm plotting fx versus x, or ft versus t. I have left out the rate values from the plot. The yellow line, which, what do you think is the parameter corresponding to that? What's a parameter for the distribution shown in yellow from these 4? And why? 4, okay. So lambda is equal to 4 here. Why? You can exactly you can reach to that conclusion with like multiple ways of thinking about it, right? First thing, let's see, lambda e to the minus lambda x, right? Let's look at 0. At 0, what happens to my function? It will be lambda times e to the minus or e to the 0, right? It will be equal to lambda. So at 4, I'm starting here, right? So that will be the first way. The other way, remember, we said mu is equal to 1 over lambda, right? Which of these has the largest mu? Obviously, the red one has the largest mu, right? Because it's more spread out to the left, or like it has a heavier tail, right? So it has a larger mean, which means that it has the lowest rate. Does all of these make sense? So this one will be 0.5, and the yellow one is 4. All right. But then regardless, we only have one parameter, right? So when I shift the parameter, it only changes the slope with how fast your distribution is coming down, right? It doesn't change the shape. They always look like this, right? All right. So it's your turn. Go through this. It will be very quick. Tell me what you get for this probability that I'm asking. What did you get? 0.9. I got 0.9 too. Okay, so let's start. First things first, I'm only giving you the mean, but you can calculate the rate from mean, right? So the rate will be what? 1 over mu, which is 1 over 240. Then the question wants, what is the probability that the set will complete the mission without failure, right? So it means that the probability that the failure happens needs to be after 24, which means I'm interested in reliability at 24, right? The function for reliability is e to the minus lambda, 1 over 240, times x, which is 24. So e to the minus 0.1, which is 0.9. Make sense? Okay. All right. So some of you may not be familiar with these functions. Let's go through them very quickly. A lot of the things, again, you can bring your laptop to class, right, for your exam. So I want you to be able to use R to calculate all of these. Then you would only show me the command that you use with the particular values that you used, and then you write the final answer. There's no, that's what I want from you, right? Again, you are welcome to use equations, but it's going to be slower. So why would you? So let's go through. That's why now we want to go through all of the formula or all of the commands that we can use in R to calculate eventually question similar to the one last slide. And then we're gonna go through exercises in class to make sure that it's clear to you how to use these commands. All right. So if I want to calculate exponential distribution, these are the 4 functions or commands I can use in R. So the first one is DEXP. This one gives me the density, right? You rarely use this to calculate things because typically what are we asking for? Reliability, time that unreliability, right? PDF, CDF. This will give you the density curve. So if you want to plot something, you would use this one, right? DEXP. The second one is the one that you typically use, but in different formats, PEXP, right? That gives you the cumulative. Okay, let's talk about this value for a second. Rate is equal to 1. Remember, we only have one parameter with exponential, right? Rate is the only parameter. The default value is 1. That's why if you call DEXP with just a value x, right, it will work because it is assuming that the default value is given. So the default value, it uses the rate equal to 1. If you want to change the rate, you just explicitly mention rate equal to something, or the second component in your function will be a value that's not 1. All right. So with the same logic, this is the default value for PXP, right? This is my distribution. This is called the lower tail. This is called the upper tail, right? Lower on the closer to minus infinity, and upper is the closer to plus infinity, right? So the default value with PXP is lower tail is equal to true, which means that this function, if you use it with default value, it will give you the CDF, right? It accumulates up to something. If you want reliability function, what should you do? You can use 1 minus this function, or what else? You can change the default, right? You can change this true to false, and it gives you the upper tail. So you can do it 2 ways. Either 1 minus PXP, or you use PXP itself and then set lowercase equal to false, or lowercase equal to capital F. And it works. It gives you the reliability. Okay, REXP, we're not going to use it for a while, or maybe not that extensively in this class. REXP is for simulating numbers based on exponential random variable with a given rate. And then QXP comes much more handy with normal and log normal, which we are going to see in a second. But they essentially give you, the way we use it in our class, it gives you back the time corresponding to a given probability, right? So it essentially gives you design life, right? So, okay, so now let's look at a couple of examples. First, we look at this example from last slide. and then look at a couple more to see if you understand all of these functions correctly. Okay. So first, let's use R to calculate the last exercise. So what did we want? We wanted reliability at 24. Then my rate was 1/240. Okay, take a second and tell me what I should type if I want to get that value from last slide. Any takers? What did you say before EXP? What was the P? Okay, so I want PXP. All right. Oops, everything is caps lock on. Okay, P EXP. All right. What is my X? What's the time at which I'm interested in my reliability? 24. What is my rate? 1/240. And then what do I want? Do I want CDF or do I want reliability? Which means I should say lower tail equal to false. Perfect. That's it. It's quicker than going through calculations, if you ask me. Absolutely, because we are interested in reliability function, right? If I wanted to use this, will give me CDF, right? Or this, true, right? This gives me CDF because it gives you the cumulative on the lower side, right? Which imagine the distribution, right? The lower side essentially gives you, when you're accumulating up to a point, it will give you CDF. So you could essentially go for 1 minus this value, right? This will give you the upper tail, which is the same as making lower tail equal to false. Make sense? All of these are acceptable, right? You can go 1 minus that, or you can use the upper tail, right? We are not picking in terms of like how you use the commands, as long as you get the final answer. Okay, all right. So now let's understand what QAXB does, right? Okay, so the question that I'm asking you is in the same function, right? Put this value, 0.09048,374, which look here, it's the same number as what we got as our reliability, right? So what do you think if I call Q, if I call the quantile corresponding to this value, what do you think I'll get? 24, right? Let's check. It exactly gives me back 24. So you can think of them as the inverse. So one will give you, for instance, f of x. The other will give you f inverse of x, right? F minus 1 of x. Or one will give you r of x. The other one will get all r minus 1 of x. So because I set my lower tail to be equal to false, it essentially gave me back the design life, right? If I hadn't set that equal to false, it would give me the time corresponding to the CDF. So again, because typically we use this function when you are interested in design life, you have to make sure that you set lower tail equal to false. So is the relationship between P and Q clear? Okay, good. All right. So you can also use, okay, I mentioned that you can use DEXP for plotting, right? Look at this function, 0.5 times e to the minus 0.5t. That is exponential function with rate parameter 0.5, right? Okay, so I can use the function curve and DEXP with x rate 1/240, x 1/240, right? This is my function, this is my curve, and I'm plotting it with command curve. So this is it. But then let me make it a little bit more clear by expanding my domain, maybe more. There we go. Actually, I wanted to plot 0.5. That's why it doesn't look good. There we go. Right, so you can quickly plot any distribution you're interested in with DXP. Okay. REXP gives you back normal random numbers, or sorry, exponential random numbers. Let's say I'm generating 1,000 of these numbers with let's say 0.5 again, with rate 0.5. So all these 1,000 numbers are drawn from exponential random variable with rate 0.5. If I plot a histogram of it, you should be able to see the trend and everything. This kind of makes sense? How the four functions work? REXP, DXP, PXP, QXP. All right. Any questions? Good. All right, let's quickly look at the hazard function for exponential. Tell me what is the hazard function? Let's calculate it. It's lambda x is equal to f of x over r of x. F of x is lambda e to the minus lambda x, right? And r of x is e to the minus lambda x. Obviously, things cancel. I'm left with constant lambda. Right? So I get constant hazard function, CFR. All right, exponential distribution is the only continuous random variable that has always constant hazard. It is unique in that sense. So now, if I'm asking you a question, instead of telling you that, oh, I have a random variable with such and such rate, I can tell you that I have a constant hazard of a function with a constant hazard 5, right? This means that I have an exponential random variable with rate 5. So I can essentially tweak my question now, right? Because I know that it's unique. Exponential distribution is the only random variable with constant hazard. Continuous random variable with constant hazard. Make sense? Correct? So here's an example. A resistor has a constant failure rate of 0.04 failures per hour. What is the reliability? Simple, right? E to the minus lambda. Oh, do I keep writing? Oh, lambda t. So this is t, and then my lambda is 0.04. Right? I'm on this page, so I'm going to just use this. But you could use R. So you're going to get 0.367. If you're using R, you should be using PXP of at 25 rate equal to 0.04, and blue I say is false. All right, so let's look at the second part. If 75 resistors are tested, how many would be expected to be failed or to be in the failed state after 25 hours? Okay, the first part definitely asking about exponential random variable, right? What about the second part? What's the random variable that I'm interested in the second part? Think about it for a second. See if you can calculate that value. And let me know if you have any questions. Anyone has a suggestion? 75 by what? 1 minus 0.3678. So that is correct. But why is that correct? This is the value that I want. Can you defend it? Okay. No, I'm asking you if you can defend why you're allowed to multiply 75 by that reliability, and then be sure that you're calculating the correct number. So this should remind you. I mean, the answer is absolutely correct. But this is essentially binomial distribution, right? That's why it's correct. You're calculating expectation of a new random variable y, and this is n times p, right? Let's look at this. You have 75 trials. They're all independent of each other. They all result in failure or success with a constant rate of success or probability of success, right? Which is this reliability. So this is why that is correct. If I ask you for variance, it may not have been as intuitive to just multiply 75 by that reliability. But then if you could argue your way that, oh, this is like actually binomial distribution, then you would know that this is np1 minus p, and you could easily calculate the value. Does that make sense? How we are switching from one random variable to another type of random variable, but by asking different questions. So this is kind of important, but again, very, very simplistic on the surface, but I want you to be able to like argue why you're using a particular random variable. Okay, great. Any questions? Okay, all right. Let's recall the radar problem. We calculated reliability. It was 0.9. Now I'm changing the question a little bit. So I'm saying that suppose the radar is still working without any failures when the mission is over, right, in 24 hours. What is the probability that it will be failure-free for another 24 hours, right? This is conditional reliability 101, right? So I'm asking R24 given 24, right? Makes sense? So this will be R48 over R24, right? Okay, e to the minus 48 times lambda, let's say, 48 times lambda over e to the minus 24 times lambda. I'm going to simplify e to the minus 24 times lambda, which is the exact same thing as this. So this is 0.9. So essentially, it didn't matter, right? The reliability function didn't change. It didn't matter that it had worked for 24 hours. Right? This should ring a bell. Everybody familiar with memoryless property of exponentials? Okay, so again, conditional reliability. If already 2 units of time has elapsed, right? And I'm interested to see what happens in the next s units, right? This will be reliability of s plus t over reliability of t. This is e to the minus lambda s plus t over e to the minus lambda t. Things cancel. This will be e to the minus lambda s, which is reliability of s. So essentially, t didn't matter, right? Right? Can I go? All right. So essentially, some of you have seen this. I've argued with the picture before for some of you. So if I have, let's say, a t here and another s time units here, right? So from this equation, so essentially you're scaling this area over this larger area, right? And you're saying that is always the same as if this is my S of the green area over the total area, which is 1, right? And if you move this T, if you shift it, right, let's say I pick, it's another T prime here, right? And this is my S. This ratio of this to this always stays the same. So that regardless of where that T is, that ratio always stays the same, right? Which is pretty unique. And again, exponential random variable is the only continuous random variable with memoryless property. So it's a very unique property that only exponential distribution has. Okay. Any questions? Perfect. So quickly about failure modes and how it relates to, and like a special case where it relates to exponential random variables. Components can fail because of different reasons, because of different modes. Let's say, for instance, I have a component, it can fail because there's a filament breaking in it, right? Or maybe there's a battery leak, or maybe it fails because of overheating. They can fail from different array of reasons, right? Sometimes these reasons are independent of each other. So if I'm thinking of a connection, right, input output. If there is, and then let's say that I have failure mode A, failure mode B, failure mode C, right? If none of them happen, then I can essentially have a line for connecting my input to output, right? Which means that my component is still functional. But if one of these failure modes occur, then my component fails, right? Because of that failure mode, but ultimately it fails. So if they function independently, I can essentially put them in a line like this and say that, okay, so if one of them fails, my component fails. So in that case, my system is reliable if none of them fails, right? So I'm essentially using again another and. If it doesn't fail because of a component failure type or mode 1, if it doesn't fail because of mode 2, if it doesn't because of mode 3, right? So if I want my component to be ultimately reliable, if I have independent failure modes, then I can multiply all of the reliabilities of individual failure modes and get to the ultimate reliability that I'm interested in. Okay, so what does that mean in terms of exponential random variable? Because again, it has a lot of special properties. So let's look at that. I'm interested in reliability, ultimately interested in the reliability of my components, and then it can be calculated as the multiplication of individual reliabilities with respect to different failure modes, right? Okay, so let's write that e to the minus lambda 1 t, right? That's the reliability with respect to failure mode 1. E to the minus lambda 2 t, e to the minus lambda 3 t, all the way to e to the minus lambda n, let's say t, right? But then I can essentially multiply these and I would get something like that. Lambda 1 plus lambda 2 all the way to lambda n times t. If I replace that long summation with a simple lambda, e to the minus lambda t. What can I say about the reliability of my component regardless of the failure mode? How is this distributed? Another exponential, right? So my overall, my component has the time to failure that's distributed according to summation of LIs. So if I have a component that can fail independently because of an array of failure modes, each of which is exponentially distributed, right, or has constant failure rates, my component overall has a constant failure rate. What is the rate? The summation of all of the individual rates, right? Which I can also calculate the mean for that, right? So the expected time to failure will be 1 over the summation of lambda i's. So again, if I have exponential, I know a lot about the different properties. It has memoryless property, it has CFR, constant failure rate, and also if I have a component with individual failure modes being exponentially distributed, then ultimately my component fails with an exponential distribution. Okay, so here's an example for you. All right, what did you get for reliability at 20? 0.71. Okay, so how did you calculate that? Exactly. So let me break it into two steps. First, I find the overall rate of failure by adding the two rates, right? And then I use that in my equation, e to the minus lambda times 20, and I get the same thing that you got. Right? And mean time to failure is just simply 1 over this, 1 over the rate, right? 1 over lambda, which is 58.8. So we already know a lot if we know things are in exponentially distributed, right? They're very, very good distributions to work with. Right. Any questions about exponential? We're moving on. Okay, another quick digression. So it is a distribution that's very closely related to exponential is Poisson, right? You may have heard of that connection. So we said the time to failure are exponential. I want to draw something. So we said the time to failure is exponential. But let's say every time the component fails, we either replace it with a new component or we repair it to as good as new, right? So this is time to failure, exponential lambda, right? Exponential lambda, exponential lambda. And why are they of different length? Because essentially I'm saying that I'm randomly, each component may present a random amount of time that it survives, right? Even though they come from the same distribution. Exponential lambda. The number of failures, if I, at any point in time, t, I look and see, oh, how many number of failures have I had so far? Then that comes from Poisson distribution, right? So they go hand in hand. If the time between events are exponential, the number of events up to some time t is Poisson distributed. So the formula for that is like this. The probability that by time t, the number of failures is equal to n is equal to e to the minus lambda t to the n over n factorial. And it is 1, 2, all the way to infinity. Expectation is lambda t, which is the same as variance. And obviously, Poisson distribution is discrete, right? Because they have zero number of failures, one number of failures, two number of failures, right? It's discrete. All right. So go through this and let me know if you have any questions. So I'm going to just quickly write part one, right? The rate is here. This is lambda. This is my rate, 2. And then time is 1 year, right? Coming year, t is 1. And then it says no failure, so n is 0. So probability that x1 is equal to 0 is going to be e to the minus 2, 2 to the 0 over 0 factorial. That's it, e to the minus 2. Right? Okay, second part, right? Let's think about it. I'm not going to give the answer right away. So first thing, it's a 2-year period. So your t is different. T is 2. But then ask about 4 or more failures. What do we know about Poisson? N goes from 0 all the way to infinity, right? So you can have 4 failure or 5 failure or 6 failure or 7 or 8 or 9 or 10. You cannot count all the way to infinity. You cannot possibly add all of them. But what do we know? It's a probability distribution, right? So if it's a probability distribution, the sum of all of the individual events that can happen, right? It should ultimately sum up to 1. So I can use complements. So I can go 1 minus the probability that nothing happens, and 1 happens, and 2 happens, and 3, and that's it, right? 1 minus 0 all the way to 3 will be equal to 4 or more. Does that make sense? Okay, so if that makes sense, let's go through it. So first, lambda t is equal to 2 times 2, 4. So I'm going to go the probability that x, or the number of failures, whatever it is greater than or equal to 4 is equal to 1 minus the probability that x2 is 0 minus the probability that x2 is 1 minus the probability that x2 is 2 minus the probability that x2 is 3. 2 minus the probability that x2 is 3. Perfect. So with 1 minus e to the minus, right, 4 to the 0 over 0 factorial, e to the minus 4 to the 1 over 1 factorial, minus 4 to the 2 factorial, e to the minus 4 to the 3 over 3 factorial. And that's it. If you do the calculations, I think you'll get 0.57 as the ultimate value. All right. Good. Any questions? Okay. All right. Let's go through a little bit more and then we take a break. Let's start Weibull. Right? You remember what I said about Weibull when we started going through life data analysis? I said it's so popular, it's so versatile in reliability engineering that essentially life data analysis is sometimes called Weibull analysis. Right? Okay, so this is just your kind of pay attention kind of thing that like Weibull is very important. All right. So Weibull is very versatile. I mean, see in a second why it is so versatile. And it's been used for modeling a lot of different time to failure for different components. There are 2 versions of Weibull distribution. We're going to focus on the 2-parameter Weibull distribution. But you're going to see that you already know, if you know the 2-parameter, you know the 3-parameter. We're going to establish it in a second. So Weibull has two parameters for the most part, right? You're going to work with this. It has a shape parameter and a scale parameter. Shape parameter, we typically show it with beta. Scale parameter, you may see it with eta or with theta. Okay. With the 3-parameter, the other parameter is the minimum life, which typically is shown with T0. And that's kind of the location parameter. We're going to see in a second again why. Okay. So Weibull 2-parameter shape and scale. Okay. So this is how Weibull density looks like. It's not as straightforward as exponential, even though it has an exponential part into it, right? E to the minus t over eta to the beta. Okay, so first, T is positive, so y-bar is a positive random variable. Beta and eta are also positive. Okay. So these are the basics about y-bar. All right. So first question. I want to write the 3-parameter y-bar, right? I want to add a minimum life. Let's say this is my y-bar, right? I have this PDF. This is ft. Y-bar, we said it starts from 0, right? I want to have the same distribution, but now with a minimum life of t0. I want to get the 3-parameter y-bar. How would I change the 2-parameter y-bar? Let's write it quickly. How would I change this function, the 2-parameter y-bar, to get the 3-parameter y-bar? How would you change that? Add, you know? So we are changing this t, these t's, right? So if I change t to be t minus t naught, or t minus t0, do you agree that I accomplished that? Let's see what happens. Essentially, my t will be greater than or equal to t0, right? Because that's the minimum life that I'm interested in. If I set my t to be equal to t0, then I will have t0 minus t0, that will be 0. So it's the same thing. So if I'm shifting my distribution to the right, I have to subtract that value from it. That's it. Right? So if I replace t with t minus t0, I get 3-parameter y-bar. Is that clear? So that's why we are not going to focus on 3-parameter y-bar, because I trust that if you can work with 2-parameter y-bar, you can essentially work with 3-parameter y-bar. That's the same thing. It's just t minus t naught instead of t. So we're not going to worry about the extra parameter. So this is just for FYI. But this is a more important, interesting part, reliability function and the hazard function. So this is the reliability function. Let's calculate the hazard function from it. What is the hazard function if this is my F and this is my R? You know how to calculate hazards, right? F over R. So look, it's very simple. The last part of F cancels completely with R, right? And I'm left with beta over eta of t over eta to the beta minus 1. So that's my hazard function. Okay? But this hazard is very special. Let's look at 3 cases. Beta equal to 1, beta greater than 1, and beta from 0 to 1. First, beta equal to 1. What do you observe? What is my hazard function if beta is equal to 1? I want somebody from this part of the class to answer. I can wait for you to write. 1 over eta. That's it. Okay? So do you notice anything? 1 over eta. Exactly. So you guys said the same thing. It is constant hazard. CFR. Oops. How do I do this? Okay. All right. So we have CFR, which means exactly as Wesley said, it becomes exponential function, right? It reduces, y will reduces to exponential function when beta is equal to 1. Okay, interesting. Now let's look at beta greater than 1. What do you notice? What kind of behavior does it show? Is it IFR, CFR, or DFR? increasing, right? Because it's greater than 1, right? One part cancels with that. It will be something that's greater than 0, right? So so it will be a constant times t to the something that's greater than 0. So if t increases, the whole function increases. So it's IFR. And with the same logic, when beta is between 0 and 1, this is DFR. So here we go. One distribution can present DFR, IFR, and CFR behavior. That's why it's so versatile. That's why it's used so widely, right? Because depending on the parameters, it can capture a lot of different behaviors. Right? So that's why it's so important in reliability engineering. Very versatile. All right, so let's take 10 minutes. Let's be back about 6:35. And let's go through this example. If you are here, you can start right now. If you want to take a break, you can take a break. We're going to look at it in about 10 minutes. Sure. All right, let's look at it. So here's the reliability function, right? You have to know what we mean by shape parameter and which one is a scale parameter. So this is the only thing you need to know to be able to do this. And you should know that shape is beta and scale is eta, right? And if you know that, then you're set. So the first one wants reliability at 200, e to the minus 200 over 300, the whole thing to the power of 2. Okay, and you get 0.6412. Second part wants the probability of failure. You have already calculated reliability, so it will be 1 minus that. Right? 1 minus r of 200. This will be 0.3588. Perfect. Last one wants design life. Okay, that's simple. So I want the t where that is equal to 0.9. So if you have that with Weibull, t will be equal to eta times minus L logarithm of the reliability of interest to the power of 1 over beta, right? And here it will be 300 square root of minus ln of 0.9, because that's the reliability of interest. Which will give us 97.38 marks. Logarithm minus ln of 0.9. Is that what you're asking? Which part? This? Okay. This is equal. Let's calculate it. It's equal to e to the minus t over eta to the beta. Right? This is equal to r. I took the logarithm on both sides. This will be minus t over eta to the beta is equal to ln of r. Right? And the rest, I just reorganize it, get t. Makes sense? Is that clear? Good. Yes, we're going to do it in a second. Yeah, that's what we're going to do. But you can follow the math, right? No problem. Okay. Any questions? All right. So let's look at it in R. Exactly. That was a good segue. All right. So the same formula, the same kind of commands. D Weibull, P Weibull, R Weibull, Q Weibull. Okay. So the first part wants, the first one wants reliability. What should I use? P Weibull, right? Okay, P Weibull. What is the first number that goes in there? I want the reliability at what? 200. Okay. What is my scale? 300. And then my shape. Oops. Shape is 2. Shape is 2. And because I want reliability, I will go with lower tail. Equal to false. Yes, just give me a second, sorry. I need to open a new window. Okay. All right, there we go. Good. So you enter the value, shape, and scale, and then set your lower tail to equal to false if you want reliability. Make sense? Okay. Second part wants the failure. So you set lower tail equal to true, or you just completely ignore that part because it's the default. Okay, so you get 0.37. What should I use for the last one? I want to design life. Exactly. And then because I want design life, I want reliability, right? So lower tail needs to be false. Then what goes in here? The reliability of interest, right? Right? That's it. It's much quicker. Just need to put in the numbers in the right order. Is it clear? Anybody has questions? No question? Pretty good? Okay, perfect. All right. All right. So now let's go through a few curves to just look at the impact of parameters visually, like what they mean. So here I'm fixing eta to be 2 and I'm varying beta. Okay, what do you notice? So first, remember eta was the scale parameter and beta was the shape parameter. What do you notice if as I'm fixing eta and I'm varying beta and I'm plotting f? You see how it changes shapes? When my beta is very small, like less than 1, it looks like an exponential distribution, like the red line. But then for larger betas, as I increase beta, you see how it becomes more normal looking, like normal the distribution, right? So fixing eta and changing shape parameter actually changes the shape of the distribution. Okay. So now I'm plotting for you hazard function for the same 4. What do you notice about the hazard? How is the red line different from the other 3? Yeah, the red line is decreasing whereas the other 3 are increasing, right? So now let's look at beta. You see how beta is less than 1 for the red line? We said we're going to have decreasing hazard rates, right? For beta less than 1. And it's decreasing. And for beta greater than 1, we said it's going to be increasing, and here it's increasing. So for beta equal to 1, we said how would the hazard function look like? Constant. Okay, so what the constant value was? You remember what we got? 1 over eta. Eta is 2, so 0.5. This is it. So this is for beta equal to 1. Right? Okay. So here is a summary. So when beta is less than between 0 and 1, the PDF is similar in looks to exponential. It's not quite exponential, right? But similar in looks to exponential, and it has decreasing failure rate. And then with beta equal to 1, we have exponential or CFR, and with beta greater than 1, we have IFR. And the distribution kind of looks like normal distribution, right? And becomes more symmetric as beta increases. Okay. So now let's fix beta and look at variations in eta. You remember beta was shape and eta was scale. Look here. As the scale parameter increases, we get more spread, right? Which is what's supposed to be for a scale parameter, right? So here I was plotting lowercase f, right? I was plotting density. Now I'm plotting reliability function, right, as a function of eta. As eta increases, what can you tell me about beta? Oh, sorry, about R. Let's look at a snapshot, right? Let's look at, for instance, this line. Here with the red, eta is 0.1, 0.5. Then with the blue is 1.5. With green it's 2. With yellow it's 4. So as eta increases, what happens to R? R increases, right? This point, this point, this point, this point. So as eta increases, R increases. Okay. Now let's look at CDF. Okay. So here is a CDF. Then I'm fixing eta to be equal to 2 for the 4, right? This is eta equal to 2. look what is happening here. Let's see if it exists if I change my eta. Is eta equal to 4? Eta equal to 6? What is happening there? Why all 4, regardless of beta, go through that point? What is that point? Looks strange, doesn't it? First, let's look at the x-axis. Here, what is the point where everything crosses? What's t? T is 2. What about here? 4. Here. Now look at eta. 2, 4, 6. So that point corresponds to the value of eta, right? So here, eta is 2. Here, eta is 4. Here, eta is 6. And the point happens at 2.246. What, right? But what happens to f? F stays the same, right? If I draw a line here, a little bit higher. If I draw a line here, and here, and here, right? The same height. Okay, so let's look at f or r. So the function f, ft for Weibull, right, is equal to 1 minus e to the minus t over eta to the beta, right? The t that causes this disturbance, where that or like whatever this anomaly or behavior, is where t is equal to eta, right? Let's set t equal to eta. What do you notice for f of eta? What is that equal to? Yeah, 1 minus 1 over e, right? Which is equal to 0.632, which is the point we marked, right? So regardless of the value of beta, at eta, I know what my f is. Also, I know what my r is, right? This is an interesting property of Weibull, which will come handy when we are going to use Weibull plots, hopefully next class. This is the point that like people used to use to be able to plot these plots, right, or probability plots, and we're going to get to it. But it's an interesting property. Okay, so let's summarize. Eta is referred to as scale parameter or characteristic life. Eta influences the mean and the spread. Reliability at a given point increases in eta. Eta has units identical to the failure time. You remember we marked eta on time, right? Eta equal to 2, eta equal to 4, eta equal to 6. And f of eta is 1 minus 1 over e. All right. So to be able to calculate mean and variance of Weibull, we need to quickly look at gamma function, right? Not gamma distribution, gamma function. And in R, you can use gamma x to calculate it. And here is the formula. So just let's get an understanding of how the formula is, what the formula is. So what is gamma 1? Let's see, gamma of 1 is equal to 0 to infinity. I'm setting x to be equal to 1. Y to the 1 minus 1, or y with y to 0, this disappears. This will be 1. E to the minus y dy. Okay, what is that value? That's equal to No one? -1? +1? Why? Defend your answer. Okay, so you're integrating. Okay, so you're integrating. Can you just look at this without integrating and tell me what the value is? Okay, I have a chocolate for that. I understand. If you integrate, you're going to calculate it and it's going to be 1. So the answer is 1. I don't have any problem with the answer. That's perfect. But only looking at this, can you argue why this is 1? It is exponential distribution. What's the parameter? Exponential distribution with what parameter? All right, whoever completes that answer will get the chocolate. Exponential distribution with parameter what? Look at it. What's the parameter? Who said that? What did you say? Why? Okay. No, still have a chocolate. 1. All right, you completed. Can you pass it? That was very stressful. That was intense. 1, right? Exponential distribution with rate 1. Exponential distribution lambda e to the minus lambda t, or lambda e to the minus lambda y, right? Lambda is equal to 1 here, right? And the area under the curve is 1. So that's why when looking, you know that it's exponential distribution with rate 1, you're integrating it, but you already know that it's a distribution, so the area under the curve should be 1, right? Oh, that was just a quick exercise. Let's look at this one. Lambda x, if it is equal to x minus 1, or sorry, gamma x is equal to x minus 1 times gamma x minus 1. So if n is a number in Z, then you can write this as gamma n is equal to n minus 1 times gamma n minus 1, right? And this is equal to n minus 1 times n minus 2, gamma n minus 2, right? And so on. And if you write this recursively, you're going to get n minus 1 factorial. So if you get 1, or if you get an n that is like a countable number, it's like from the natural numbers, then you can calculate it by hand. Otherwise, you have to use R. And why do we need them? Because for mean time to failure and variance for Weibull distribution, you need the gamma function, which again, super simple. You just call gamma with the value in R and calculate it. So is it clear? Those are the functions. Weibull is a little bit more complicated than a lot of other distributions we've seen. So the mean and variance are also a little bit more complicated. Any questions? All right. Okay, let's quickly go over normal to just refresh your memory. So normal, everybody has seen it. 2 parameters, mu, sigma. This is how the distribution looks like. Mean is going to be mu, variance is going to be sigma squared, and we show that the notation for that is xn. Pay attention. This is sigma squared in the first in the second part of this piece of notation, right? Not sigma, it's sigma squared. It's variance that we put in the second part. Okay. All right. So we all know that it's bell-shaped symmetric. By changing mu, we change the location. So mu we'll just shift the distribution, so it's a location parameter. And sigma changes the spread, so that's the scale parameter. Okay. But then they don't change anything. The area under the curve always is 1, and it's always symmetric. Right? Okay. All right. So quick, sort of quick images again, or plots again. So here is the distribution. I'm setting mu to be equal to 0. and changing sigma, changing the spread. Okay. Here, I'm plotting for you capital F, right? And obviously, you know what this point is. What is that point? 0.5, because this is essentially we have a symmetric distribution, right? So it's the median. So this point is the median, but the median is also the mean because it's symmetric, right? All right. So yeah, so if I change mu to be equal to 1, again, median is going to be 1, right? Makes sense? Good. Okay. So now hazard. Look at the hazard for normal. What do you notice? It's always increasing. So normal always has IFR. It cannot model DFR. It cannot model CFR, right? It's always IFR. Okay. So normal is, it cannot be, we cannot integrate it, right? It's like complex looking function. We cannot really integrate it. So that's why they came up with the standard normal, which is when mu is equal to 0 and sigma is equal to 1, right? And the CDF has a particular notation, y of z, and then that is the cumulative function. That's essentially equivalent to f, capital F. But it's so versatile, or it's so commonly used that we are gonna not use the F notation for it. We're gonna use phi notation for it, right? Okay. So everybody familiar with that. So and everybody familiar with table. We are not gonna use table in this class. We're gonna use R. So we're putting that aside, but it's gonna be quicker. I promise it's gonna be easier. Okay. So if you're transforming normal to standard normal, this is the way to do it. X minus mu over sigma. And then that's why this is gonna be, so if I'm interested in f of x, where x is regular normal, right? Normal distribution, I'm gonna have phi of x minus mu over sigma. So this is the relationship between normal and standard normal. This is a transformation. But again, we're not going to use that. We're going to use just R. So let's look at that. Any questions? Okay. So with everything again that we've seen, D norm, P norm, R norm, Q norm. So let's look at these couple of exercises. So use R to find reliability at 96.97 if we have X from a normal distribution with 120 and 196. So help me out. Let's calculate that. I'm calculating reliability, right? So what is the function that I need to use? P. Okay. So I'm going to use P norm. What do I need with P norm? I'm gonna need. Oh, this is the one. So P norm. I want the reliability at 96.97, right? 96.97. Perfect. What is my mean? 120. What is my standard deviation? Because the function gets ST. The standard deviation is what? A square root of, exactly, a square root of 196, which is 40. Okay? And I want reliability, right? So I want the lower tail to be false. That's it. Make sense? Good. Any questions? Because this is what you need to do in test, in homework, and everywhere. All right. So we got not the reliability to be 95%. Okay. Now let's look at the second part. Now I want to find the design life if the reliability of 95 is required, right? I'm gonna need to use Q norm now, right? Everything stays the same. The value that I put in is 95.95. Make sense? Again, you have the same mean, 120. You have standard deviation goes in there, square root of 196. And because you are interested in reliability, you have to set the lower tail to be equal to false, which obviously is going to give you back the number that we put in last time. Make sense? Okay. Super easy. All right. So use that to calculate this. All right, so it's essentially the same question as last time. This time, instead of giving you the variance, I'm giving you standard deviation. I'm doing one step extra, right? So it's the same thing, but instead of a square root of 196, you have to just put in standard deviation, and that's it. This is the same answer, right? But now this is in units of hours, right? I want to transform in units of days, but then my days are 12 hours, right? So I have to divide this by 12. Okay, which gives me like 8.08. So is it 8 days or 9 days? If I want that reliability, I have to round up or down? Down, yeah, right? I have to round down to make sure that I meet my desired reliability. Okay, that's it. So you get the answer, divide by 12, and then round down, so the answer will be 8 days. All right, so moving on to log normal. Any question about normal? Okay, good. Log normal, another complex looking density function, right? This one has two parameters, right? S and T med, which is the median. Let's see. S is the shape parameter, and T med is the scale parameter. This is a positive distribution again, positive random variable. But okay, so this is like one of the two different ways of showing the density. As the name suggests, this distribution has something to do with normal distribution, right? It's log normal. So this is the relationship. If random variable t has a log normal distribution, logarithm of t has a normal distribution. Okay. So alternatively, we can write the same f using the parameters of the corresponding normal distribution, right? If the corresponding normal distribution have parameters mu n and sigma n, right? It's based on normal, right? Mu n and sigma n. We can write the distribution according to the second equation. Okay. So now let's compare the first equation and second equation and see if there are any relationship between them. Let's compare sigma and s. Do you agree that they are the same thing? Let's look. Here I have 1 over s times t times something, and then here on the bottom I have 1 over sigma n times t times something. They're very similar. So s is actually equal to sigma n. Okay. So what else do I have? What is mu n equal to? So in the top I have 1 over so here I have minus 1 over 2s squared times something, and here I have minus 1 over 2 sigma n squared times something. So those somethings, if they're equal, then I have the same equation. I know that they are the density for the same random variable, right? So that it's not a surprise that they are the same. Okay, so let's compare this part with this part. So I have ln in both of them. So here I have ln of t minus ln of t med. Here I have ln of t minus mu n, which makes mu n equal to logarithm of t med. Or alternatively, I can write t med is equal to e to the mu n. So that is the relationship between the two different ways of presenting the distribution. So this is where you have to pay attention, because I may give a question when I'm giving you scale and shape parameters, or I may give you a question where I tell you that the corresponding normal distribution has these two parameters, right? You can go from one, you can essentially switch from one to the other one, and then just do your calculation. But you have to have these equations in mind. S equal to sigma, so sigma n acts as the shape parameter, and mu n acts as a scale parameter, right? Because just a logarithm of the other one. It preserves shape. All right. And mu n and sigma n are the parameters of the corresponding normal, right? Okay. Hopefully it will make sense in as we go through it. But any questions? Okay. Just a relationship. It's not a big deal. All right. So let's look at a few plots. So first, I'm plotting for you the density function, right? Notice that this is a positive. It's a positive distribution, okay? A positive random variable. And sigma n kind of acts like a shape parameter. So here I have something that kind of looks like exponential, and here I have something that looks maybe more like one of the shapes of Bible. So it kind of changes shape. Then I'm changing mu n, because this is mu n, right? This is the mean of the corresponding normal. I'm working with log normal. So mu acts like a spread, right? Acts like a scale parameter. So it changes the spread. Okay. Now I'm plotting for you the CDF. So here I'm plotting for you for 4 values of sigma n, when mu n is equal to 0 and mu n is equal to 1. So again, we have a point. What is that point? What is the height? 0.5, okay? The same with here. Which means that this 0.1 is what? Immediately, if I have mean equal to 0.5, T med, right? This is the median. So this is T med, right? The same with here. This is T med. Which makes sense, right? Because, okay, let's look at this. I know mu n is equal to logarithm of T med. So if my T med is equal to 1, right, my mu is going to be 0. Agreed? The same with here. If this is almost 2.7. If my T med is equal to 2.7, its logarithm is going to be 1. Like this is E. Right? So that's the median. Okay, so this is the hazard function. So the hazard function looks very strange. It's increasing, then it plateaus, and then it decreases. All in one function. You remember with Weibull, it was always decreasing for beta less than 1. It was always increasing for beta greater than 1. With normal, we had always IFR. Here with log normal, we can model something that has increasing failure rate in the beginning, then it has decreasing failure rate. Right? So it's a different shape. Okay. So these are the mean and variance of the distribution. But here I'm using S and T med. So remember the equation we had. T med is equal to e to the mu, which means that you can, if I'm giving you S and T med, you can calculate MTTF like that. If I'm giving you mu n and sigma n, you can write this is e to the mu n plus sigma n to the 2 over 2. Right? So you can transform, go from use one type of definition to another type of definition, right? Because we know T med is equal to e to the mu n, and S is equal to sigma n. All right. The same with here. I can just transform it and write it in terms of mu n and sigma n. Okay, so again, the same with normal. Integrating this function is going to be very difficult. We're not going to integrate, right? We're going to use R. But to be able to use R, we have two ways. We can either go back to the normal part of it, right? Because we know that this distribution is related to normal distribution, or we can directly calculate it. So I'm going to show you both ways. So if I want to use the normal distribution to calculate my CDF, I have to go through a little transformation. So I have the CDF f of t is equal to probability that t is less than or equal to t. Remember that if you take the logarithm from both sides, then you're left with a random variable. This is now normal mu n and sigma n squared, right? So you should be able to write this in terms of phi, right? So it will be ln of t minus mu n over sigma n. But we also had an equation where we know that mu n can be written in terms of t med. So I can write it both ways. So this will be equal to phi of 1 over s ln of t over t med. So this is f. R will be 1 minus that. 1 minus phi of, let's say, 1 over s ln of tn over t med. Right? So you can use the standard normal. You just plug in this value, right? And then you calculate. You use R to calculate your CDF. You just need a quick transformation based on this equation. Everything is the same as normal. Or you can directly use log normal. So let's go through it using this equation, and then I'll show you how to do it with log normal. So here is the question for you. All right. So the first part is very easy, right? Just multiplying values. 5,000 times e to the minus, no minus, 0.2 to the 2 over 2, and we get about 5,100 atoms. Okay. Second part, we use the equation 1 minus phi of 1 over 0.2 times logarithm of 3,000 over 5,000, which will give us 1 minus phi of minus 2.55. Okay, so the rest is simple, right? We have to go to R. What should I put in R? Phi is standard normal. Do we know how to calculate this? Standard normal evaluated at minus 2.55. I want 1 minus phi, which means I want reliability. Is that clear? Am I losing you? I cannot read. Yeah, 1 minus p norm, or like I can go p norm minus 2.55 and lower tail f. That's it. Good. So we calculated that, the final value. So this will be 0.9946. Use p norm. Right here we are using p norm, but we can actually do it directly if we choose to. Right? We can put it directly in L norm, right? Logarithm or log normal. All right, so there is only a minor catch. We have to be careful when we are doing this because the parameters that log normal asks in R are sigma n, or like mu n and sigma n. Mu n and sigma n. So you just need to be careful. If I'm giving you, for instance, the last example, right? In the last example, I was using Tmed and S. You have to do the transformation to get mu and sigma and put it in there. So let's do it. So I would be, say, calling P L norm, right, at 3,000 when my mean log is equal to, what was the value that I had? Yeah. So I have to do transformation, right? Tmed, relationship between Tmed and mu n. Remember, I have to get the logarithm of Tmed to get my mu n. So it will be logarithm of 3,000 or 5,000, sorry. Oops. Logarithm of 5,000. The good thing is S is the same as sigma. So I just put that in. And my lower tail needs to be false, right? Because I'm interested in reliability. I got the same value. Of course, there are going to be a slightly different because I put in like up to 2 significant digits here. So I did a little bit of transport, like I lost a little bit of accuracy there. But that's it. So you can do it directly, you can do it indirectly, whichever way you prefer. They're all equally good. All right, so anything else? Any questions? All right. So have a good weekend. We're going to post homework, we're going to post quiz, and we're going to have guest speaker next class. So make sure you attend. It's going to be interesting. All right. Thank you.